Assalamu alaikum, dear students. We are going to continue our chapter related to nucleophilic substitution reaction. In previous lecture, we studied about various kinds of nucleophiles and their attack on alkyl halides, and we studied that how many different classes of organic molecules or compounds we can prepare from alkyl halide and nucleophiles. So there are two major types of nucleophilic substitution reactions. One is SN2 and the other one is SN1. In today's lecture, we shall discuss about mechanism and potential energy diagram of substitution nucleophilic bimolecular reaction. Its short form or abbreviation is SN2. Then we shall talk about stereochemistry of SN2 reactions and steric effect of attacking nucleophile, and at the end of this lecture we shall discuss about different types of nucleophiles and their attacking capability, that is called as nucleophilicity. So the extensive study about these reactions was conducted during 1930 at University College London. University College London is well known and well recognized institute. It's at number 6 university in the world. So the group leader of this research was Sir Christopher Ingold and Edward D. Hughes, and further their other lab associates, their PhD students and research fellows. They conducted extensive study to investigate the rate of reaction. Rate of reaction, simply we can say kinetics of reactions. So there are two main reactants for these reactions. One is attacking nucleophile and other one is alkyl halide. So if we talk about the net reaction is substitution or replacement of this alkyl halide, this halide by this attacking nucleophile. So we can write down the product of this reaction like ROH, and the other part is this leaving group, that is halide. So how this reaction proceeds means what is the mechanism of this reaction. So when we talk about the mechanism, there is a charge separation in this molecule. There is partial negative charge on this halide part and partial positive charge on this carbon. So attacking nucleophile will attack on this carbon, and the bond between alkyl group and halogen will break down, and consequently we shall obtain the product that we have written in the above equation, means R, and there will be OH, and further we shall get halide group that is also called as leaving group. So when they conducted series of experiments on primary alkyl halides and various nucleophiles, they investigated that this is a single step reaction. Single step mean at the same time this hydroxyl group develops bond with this alkyl group, and at the same moment the bond between alkyl and halide starts breaking. So what happens actually if we take example of CH3X. So this is a carbon, it has three hydrogens and here is its halogen part. So when a nucleophile will attack on this carbon atom, there will be a development of bond between carbon and halogen, and at the same time the bond between halogen and carbon will start breaking. So this is a stage between these reactants and products. The stage between reactant and product It may be named as transition state, or we can name it as intermediate. So how we can decide or name this state? Either it is a transition state or it's a intermediate. So it depends upon the stability of the state which is produced during the course of reaction when a reactant transformed into a product. So if the stage between reactant and product have some stability, that we can measure the stability of that state by any conventional chemical reaction or by any spectroscopic study. So that state will be called as intermediate. But if the state between reactant and product is not detectable, so it's just an imaginary state, so that kind of state will be called as transition state. So this means this state is called as transition states. It means there is no practical evidence about the existence of this state. So it means it's our imaginary or hypothetical state that in a single state there is a bond development between carbon and nucleophile and bond breakup between carbon and halogen. So if we talk about the potential energy diagram for this reaction, so on y-axis there is a potential energy that is increasing from top to bottom, and this is a reaction coordinate. So we know for a successful reaction, the energy of product is always less than reactant. If the energy of reactant is greater than product, it means that reaction will not go into the forward direction, that reaction will go into the reverse direction. So when there is a successful reaction between two reactants, in that case, the energy of product will be always less than that of reactant. So here we have two reactant. One is nucleophile that is going to attack on a alkyl halide. This is a partial positive center, this is a partial negative center. So this hydroxyl group is going to attack on this carbon. So what will happen? There will be a partial bond development between carbon and hydroxyl group, and this bond will start to break. So when there is a state where there is a case of bond development and bond formation, that state will be definitely in higher in energy as compared to reactants. So when these reactant will approach each other, they will convert into a transition state. So in the transition state, at one side there is a bond development and the other side there is a bond breakup. So this state will be higher in energy as compared to reactants. When this bond will completely form and this bond will completely break, so this will convert into a product. In product we will have bond between carbon and attacking nucleophile. This is carbon, hydrogen, hydrogen, and we have a leaving group. So here we can notice one more thing, that the nucleophile can always attack from the back side of already attached nucleophile, because this side is always occupied. The only opportunity or possibility of attacking nucleophile is from the back side. So in SN2 reaction types, the stereochemistry of the reaction is always stereospecific. Stereospecific mean If the already our existing nucleophile is at the right side, the new attacking nucleophile will be attached to a left side. So there will be 100% inversion of configuration. 100% inversion of configuration, or we can say that the product will be just like an inverted umbrella. In umbrella, you can see if umbrella is like this, but in the product side, we shall have this kind of umbrella. So the configuration will be changed from R to S or from S to R. So this is the second goal that we are going to achieve in this reaction, the stereochemistry of SN2 reactions. In SN2 reactions, there will be 100% inversion of configuration. So next point that we shall discuss in this lecture is steric effect. So now we are going to compare the reactivity of alkyl bromides for SN2 reactions. Here we have a set of 4 alkyl halides. The negative part is common, that is the leaving group, bromide, 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 but the alkyl chain is different for these 4 alkyl bromides. First one is methyl bromide, that is very much simple case. There is no branching, unsubstituted. We can simply write this molecule like CH3Br. For the second, this is a primary, but we are going to extend this carbon chain CH3 CH2Br. The first one is isopropyl bromide, means we have substituted two of hydrogens of this carbon with two methyl groups. So this is a isopropyl bromide, and the last one is tertiary butyl bromide. We have substituted all three hydrogen of this methyl group with four methyl groups. So there are three methyl groups with this carbon. So what is happening when we increase substituent on this carbon? So we can see for methyl bromide, the reaction rate is too much high. And when this carbon gets substituted with 3-methyl group, the reaction is too small to measure. So there is a trend with increasing branching or substituent on primary carbon, the rate of reaction is getting decreased. So another set for comparative analysis is here: ethyl bromide, propyl bromide, isopropyl, isobutyl bromide, and neopentyl bromide. In this case, the substitution is not directly on this carbon. Actually, we are extending the carbon chain, but the branching is at some other place. We can write these molecules like ethyl bromide, CH3, CH2, Br. For propyl bromide is CH3, CH2, CH2 bromide. For isobutyl bromide, isobutyl. So this is a isobutyl bromide. In this case, we can see this carbon atom is common for all these three molecules. Here is CH2, CH2, CH2. But what is happening? The next carbon, CH3, it is substituted with one methyl group. In this case, this carbon is substituted with two carbon atom. And for the last case, the neopentyl bromide, This is connected with three carbon atoms. For the first case, we talk about this carbon atom, and in the second set, we are going to discuss this carbon. Here, this carbon is substituted with two hydrogens, same two hydrogen. But the next carbon, this one, in this case CH3, in this case it is connected with one methyl group, it is connected with two methyl groups, it is connected with 1, 2 and 3 methyl group. Although the reaction rate is not being affected too much as we discussed in first table, here is also a decline or decrease in rate of reaction, but we can see that the branching or substitution at primary carbon affects the rate of reaction too much. So this is a steric effect, means branching on the carbon atom directly affects the rate of reaction for a SN2 reaction. So the last content of today's lecture is nucleophile and nucleophilicity. Now we are going towards the last segment of today's lecture, that is about nucleophile and nucleophilicity. So the first question is, what kind of molecules can be used as nucleophile in these reactions? So simply we can say that all Lewis bases can act as nucleophile in SN2 reactions. So we know that there are two types of Lewis bases. There are anions which carry negative charge, and there are also some neutral molecules which can act as Lewis bases. So both of these two classes can be used as nucleophiles in nucleophilic substitution reactions. For anions, we have studied multiple times the example of hydroxyl group. So it carries negative charge. So it is understood and most common nucleophile used in nucleophilic substitution reaction. The other less common types of nucleophiles are amines, phosphines and sulfides. So in amines, nitrogen carries a lone pair of electron, phosphorus also carries a lone pair of electron, and sulfur carries two lone pairs of electrons. Nitrogen and phosphorus, these two belong to the same uh, group in periodic table, and sulfur belongs to oxygen family. So here is a example that how a sulfide can take part in nucleophilic substitution reaction. So just like oxygen, it carries two lone pairs of electron, so it can easily attack on this partial positive carbon and partial negative oxygen, partial negative iodide part is cleaved as leaving group. So when it denotes its lone pair, so there will be a positive charge on this sulfur. Another type of nucleophile that is under discussion is solvolysis. In so many cases, the solvent molecules can also take part in the reaction and they act as nucleophile. So if the solvent is water, then the reaction will be called as hydrolysis. So water molecule carries two lone pair of electrons, just like this example. So oxygen can attack on this partial positive carbon and halide part will be removed as leaving group. So just like sulfur, there will be a positive charge on oxygen. So this species is not stable. So in the second stage, another water molecule will attack on this unstable species, and water molecule will abstract one of the hydrogen atom, and this bond pair will be shifted to this oxygen, and ultimately the product will be in the form of alcohols. So just like water, ethanol or methanol can also act as uh, nucleophile. So when the solvent is water, the reaction will be named as hydrolysis. When the solvent is methanol, so this reaction will be called as methanolysis. So oxygen, just like in water, can attack on this partial positive alkyl group, this bond will be heterolytically cleaved and halogen will be removed as a leaving group. There will be a positive charge on this oxygen. So another molecule of methanol in the media will abstract this hydrogen and we shall obtain CH3OR. So this class will be called as methyl ethers because this alkyl is our choice. So whatever the alkyl group in the alkyl halide, the same alkyl will be connected to this side. So simply I can pose a question to you: how can we prepare methyl ethers by SN2 reaction mechanism? So when I will specify how can you prepare methyl ethers, so you will directly go to this kind of reaction. You will write that methyl ethers can be prepared by methanolysis and you can write this reaction. So one thing is to note that this first step is SN2 reaction. This second step is not SN2 reaction. This is just Bronsted acid base reaction. Similarly, in this case, this reaction is not SN2 reaction. This is just a Bronsted acid base reaction. So here we have a table where we have mentioned 1, 2, 3, 4 and 5 categories of nucleophiles with their nucleophilicity. The first class contains very good nucleophiles. Their reactivity is 10 raised to power 5. Then we have good nucleophiles which have reactivity about 10 raised to power 4. Then fair, they have 10 raised to power 3. And then there is a weak class of nucleophiles, their reactivity is 1, and then we have very weak class that has 10 raised to power minus 2. So how can we identify that which nucleophile is more carrying nucleophilicity or nucleophilic character and which one is weak towards its nucleophilicity? So the one criteria is their size. So we know that when we move down a group, there is an increase in size. So when we move down in a group, the size of particle increases. So with that increase in size, the nucleophilicity increases. So it means this particular ion has more nucleophilicity as compared to this hydroxyl group. Similarly, when we move down from fluoride to iodide, the size of ion increases and nucleophilicity increases. So why this happens? So actually it is related to salvation of anion. This is a smaller size anion. Hydroxyl group is also smaller in size. So in the media, we use excess of solvents, either water, ethanol, methanol. As we studied at the start of this chapter, that we use mixture of water and other alcohols because mostly the salts are soluble in water and organic species are soluble in organic solvents, and we also discussed that the other option is DMSO. So it means we have excess of solvents in these kinds of reactions. So when there will be a solvent, so solvent can easily solvate these smaller size anions. So means when these anions are solvated, so though these are no more available to act as nucleophile. The solvation of iodide is less as compared to fluoride, so it means it will be easily available to act as a nucleophile. So the other thing that I have mentioned very clearly, least basic. So it means fluoride is stronger in basicity but weak in nucleophilicity, and at the other end iodide is weak in its basicity and greater in its nucleophilicity. So what is difference between nucleophilicity and basicity? Basicity is affinity of an anion towards a proton. So HF can easily accept proton as compared to iodide. So this is the case when this reaction is happening in the presence of excess of solvent. But on the other hand, if there is no solvent, means we are conducting these reactions in gaseous phase. So under those conditions, their reactivity will be reversed. In gaseous phase, there is no solvation. It means fluoride is fully available to react with alkyl halides. So we can say that in case of salvation or solvent, iodide is most reactive nucleophile, then bromide, then chloride, and fluoride is least reactive. This is the case in case of solvent. But if the reaction is happening in gaseous phase, then the reactivity will be reversed. Iodide will be least reactive, then bromide, then chloride, and fluoride will be most reactive. But most of the time, this trend is followed because these reactions are happening in the presence of multiple or single solvent systems. Thank you so much.